Hello, welcome to Module 6 on Blockchain Systems Architecture and Consensus Protocols. This lecture, Lecture 2, is on the basics in blockchain system architecture. Its learning outcomes is to understand how to construct architecture of blockchain-based applications, applying design patterns, compare different consensus protocols. More specifically, in this lecture, we will learn how to employ design patterns and reusable proven solutions to explain blockchain system development. This lecture is entirely based on the book on architecture for blockchain applications by Hugh Weber and Staples. In software systems, the design pattern is a reusable solution to problem that commonly occurs within a given context during software design. It defines constraints that restrict the role of architectural elements and the interaction among those elements. Using the pattern in an application architecture can better align it with the unique properties provided by blockchain, avoid its limitations, and achieve other quality attributes. In this lecture, we follow an established form to describe each pattern, which includes the name of the pattern, a short summary, the context, the problem, statement, and explicit discussion of the forces that make the problem difficult, the solution, its consequences, and some examples of known real-world uses of these patterns in the blockchain technology. We will speak about 4 different types of blockchain patterns: patterns interacting with external world, data management patterns, security patterns, contract structural patterns. Let's start with the patterns on interacting with external world. And here we will see 3 different patterns: Oracle, reverse Oracle, legal, and smart contract peer. Let's start with the first pattern, which is Oracle. The Oracle pattern introduces the state of external systems into the closed blockchain execution environment. Problem: the execution environment of the pattern is self-contained. It can only access information present in the data and transactions on the blockchain. Smart contracts running on a blockchain are pure functions by design. The state of external systems is not directly accessible to smart contracts. Yet, function called in smart contracts sometimes needs to access state of the external world. Solution: to connect the closed execution environment of the blockchain with the external world, an oracle is introduced to evaluate conditions that cannot be expressed in a smart contract running within the blockchain environment. An oracle is a trusted third party that provides smart contracts with information about the external world. When validation of a transaction depends on external state, the oracle is requested to check the external state and to provide the result to the validator, which then takes the result provided by the oracle into the account when validating the transaction. Benefit: the closed execution environment of a blockchain is connected with the real world through the oracle. The applications based on the blockchain can access external states through the oracle and use these external states in their execution. Drawbacks: trust. Using an oracle introduces a trusted third party into the system. The oracle selected to verify or supply the external state needs to be trusted by all the participants involved in relevant transactions. Validity: external states injected into the transactions cannot be fully validated by other miners. Thus, when miners validate transactions, including external state, they rely on the oracle. Next pattern is reverse oracle. The reverse oracle pattern describes how off-the-chain components of an existing system rely on smart contracts running on a blockchain to supply requested data and check required conditions. Many pre-existing or legal The problem is that many pre-existing or legal systems do not have direct interface to blockchain. Data or functionality of a blockchain may have to be integrated with legacy systems, but a non-intrusive approach is required, non-changing the core of the existing systems. Solution: a component that can interact with both the blockchain and existing system components is added to the system. The reverse oracle component provides broader system functionality by mediating with blockchain data and smart contract functionality. Well-known smart contract functions can be configured in the component to access blockchain functionality, or the identity of transactions on the blockchain can be made visible to the system for integration. Benefits: connectivity. The blockchain is integrated into an existing system either by configuring well-known smart contract functions to be involved, or by making blockchain transactions visible to the system for integration. Drawback: non-intrusive. It is not always possible to use a blockchain in a non-intrusive way, depending on extensibility of the existing system. Next pattern is legal and smart contract pair. The legal and smart contract pair pattern describes a bidirectional binding is established between a legal agreement and a corresponding smart contract. Problem: an independent, trustworthy execution platform trusted by all the involved patterns is needed to execute digital legal agreements. Blockchain can provide that platform using on-chain smart contract to digitize legal agreements. Solution: a smart contract is created to implement some of the conditions defined in the legal agreement. When deployed, there is a variable to store the hash value of the legal agreement, but initially has a blank value. The address of the smart contract is included in the legal agreement, and then the hash of the legal agreement is calculated and added to the contract variable. By binding a physical agreement with the smart contract, the bridge between the off-chain physical agreement and the on-chain smart contract is established. Two-directional binding shows the intended mapping between the legal agreement and smart contract. Benefit: automation. Some of the conditions defined in the legal contract, for example, a conditional payment, can be automatically executed or enforced by blockchain. Audit trail. Blockchain permanently records all historical transactions related to the legal contract and the smart contract. Drawbacks: expressiveness. Smart contracts are written in programming languages. These programming languages might not be able to express all contractual terms or regulatory compliance conditions. Enforceability. If a public blockchain is used, there is no central administering authority to decide or dispute or to enforce court judgments. Interpretation. There might be many possible ways to interpret contract conditions and encode them in smart contracts. Ambiguity in natural language makes it a challenge to accurately implement legal terms in a way that will be agreed upon all the involved participants. Let's also speak about decision model for interaction with the external world patterns. Let's see when to decide when these patterns can be connected with the external world. When it comes to the Oracle deployment options, a centralized Oracle could be applied to collect the external state. The centralized Oracle introduces a trusted third party in the blockchain system to verify the external state. Such a centralized Oracle component becomes a single point of failure. Thus, unavailability, failure, or compromise may prevent blockchain from completing the transaction validation. To overcome a single point of failure, a decentralized Oracle consisting of multiple external servers and independent data sources could be used. In this case, the voting pattern could be used with multiple decentralized oracles to reach consensus on the external state. Thus, if the result reported by one oracle is debatable, other oracles or anyone with a blockchain account could propose a new answer and vote for the proposed result until the consensus is achieved. The direction of the data flow is typically the first factor to consider. If the data flow from the external world of the blockchain, an inbound oracle is used to transfer data from the external world to the blockchain. Depending on the initiator of the data flow, we can choose either the pull-based inbound oracle or push-based inbound oracle pattern. If the data flow from blockchain to external world, an outbound oracle can be used to transfer data from blockchain to the external system. Similar to the inbound oracles, there are push-based outbound oracle and push-based outbound oracle and pull-based outbound oracle. The former keeps monitoring the blockchain for relevant updates. Next group of patterns are data management patterns. These are encrypting on the chain data, tokenization, off-chain data storage, and state channel. Let's look to the encrypting on-chain data pattern. The encrypting on-chain data pattern ensures confidentiality of the data stored in blockchain by encrypting it. Problem: data privacy is one of the main limitations of blockchain. All the information on blockchain is publicly available to participants. There is normally no privileged user within a blockchain network. On a private or consortium blockchain, the ability of parties to participate might be limited by the consortium agreement and by network access controls, but all participants will normally be able to see the full blockchain history. On a public blockchain, new participants can join the blockchain network freely. Solution: symmetric or asymmetric encryption can be used to encrypt data before inserting data into Oracle. Benefits: confidentiality. Using encryption, the publicly accessible information on a blockchain is encrypted, so that it is not readable by anyone who does not hold the secret key. Drawback: key management. Both symmetric and asymmetric encryption require off-chain key management. Access revocation. Revoking read access is a challenge after the encrypted data has been published to the blockchain. It is difficult to ensure that a party has destroyed the knowledge of the secret key. The encrypted data on a blockchain is immutable, and so as long as the participant retains the secret key, it retains access to the encrypted data. Immutable data. Even if stored in encrypted form, the sensitive data will remain in the blockchain forever. In addition to the risk of the key compromise, the encrypted data may be subject to brute force decryption attacks at some time in the future. Key sharing. The encryption key needs to be shared before the encrypted data on the blockchain can be read. Although blockchain itself can be used in a software connector to communicate data, secret keys cannot be shared in plain form through blockchain because the shared key will be publicly accessible if being communicated through blockchain. Next pattern is tokenization. The tokenization pattern uses tokens on blockchain to represent transferable digital or physical assets or services. Problem. Tokens representing assets or services should be transferable so that they are no longer held by the original party after the transfer. The holding of a token by someone should be able to be authoritatively determined by others. Solution. Blockchain provides a trustworthy platform to realize tokenization. There are different ways to implement tokenization using platform. Native tokens exist on public blockchains, but in addition to being cryptocurrency, they can also represent other assets or services using transaction identifiers or other auxiliary data. A more flexible solution is to define tokens as a data structure in a smart contract. The smart contract imposes constraints to ensure that holding and transfer of the token support the requirements of the token schema. Benefit. Representation. Tokens implemented on blockchain, especially when using smart contracts, have a great range of expressive power suitable to representing many kinds of assets or services. Holding and transfer. Blockchain transactions record the transfer of tokens and ensure that a token cannot be double spent. The transparency of a blockchain allows all participants to inspect the latest state of token holdings. Drawbacks. Integrity. Integrity of tokens is guaranteed by the blockchain infrastructure, but bugs in smart contracts can lead to problems in the holding or transfer of assets. Legal processes for ownership. A token on a blockchain is not necessarily the authoritative source of information about the ownership of a physical asset. The owner of an asset may be entitled to sell the asset without being required to create a transaction on the blockchain. Also, legal processes such as court orders and bankruptcy proceedings can change the ownership of physical assets without any associated transaction being recorded on the blockchain. Next pattern is off-chain data storage. The off-chain data storage pattern uses hashing to ensure the integrity of arbitrary large datasets which may not fit directly on blockchain. Problem. The blockchain, due to its full replication across all participants of the blockchain network, has limited storage capacity. Storing large amount of data within a transaction may be impossible due to the limited size of the blocks of the blockchain. Solution. A blockchain can be used as a general-purpose replicated database, as transactions logged in the blockchain can include arbitrary data on some blockchain platforms. For data of big size, especially data that is bigger than its hash value, rather than storing the raw data directly on blockchain, a representation of data with smaller size can be stored on blockchain with other small-sized metadata about the data. The solution is to store a hash value of the raw data on chain. Benefit: integrity. Blockchain guarantees the integrity of the hash value that represents the raw data. Cost: if a public blockchain is used, blockchain is utilized at a lower cost for integrity of data with arbitrary size. Drawbacks: integrity. The raw data is stored off-chain, where the off-chain data store might not be as secure as blockchain. The raw data might be changed without authorization. This change will be detected thanks to the hash of the original data stored on the blockchain. However, without additional measures, it will neither be possible to recover the original data nor to prevent the change from happening in the first place. Data loss. Since the raw data is stored off-chain, it may be deleted or lost. Only its hash value remains permanently on the chain. Data sharing. The on-chain data can be shared through using blockchain platforms. Additional communication mechanisms and storage platforms are required for data sharing off-chain. Next pattern is on state channel. The state channel pattern is about transactions that are too small in value relative to a blockchain transaction fee or that require much shorter latency than can be provided by a blockchain are performed off-chain with periodic recording of net transaction settlements on-chain. Problem: the decentralized design of blockchain has limited performance. Transactions can be several minutes or even 1 hour to be committed on the blockchain. Due to the long commit time and the high transaction fees on a public blockchain, it is often infeasible to store many low-value transactions on the blockchain network. Solution: solution is to establish and agree on blockchain protocol between two participants with a deposit from one or both locked up as a security in a smart contract for the lifetime of the channel. Benefit: speed. Without evoking a blockchain for every transfer, off-chain transactions can be settled without waiting for the blockchain network to process and commit each transaction. Throughput. The number of off-chain transactions that can be processed is not limited by the configuration of blockchain, such as the blockchain size, block interval, or gas limit, and thus a much higher total throughput can be achieved than for an off-chain transactions. Privacy. Other than the final settlement transaction, the individual off-chain transactions do not show up in the public ledger. Thus, the detail of these intermediate off-chain transactions is not publicly visible. Cost. If a public blockchain is used, only the initial and final transaction incur a transaction fee to be included in the blockchain. Individual off-chain transactions do not have blockchain transaction fee. Multi-hop off-chain transactions may be charged small transaction fees to compensate for reduced liquidity of channel providers, which are typically charged as a percentage of the transaction amount. Drawbacks. Trustworthiness. Individual off-chain transactions might not be as trustworthy as the on-chain transactions because the transactions are not stored in the blockchain's immutable data store. Reduced liquidity. To establish a payment channel, money from both sides of the channel needs to be locked up in a smart contract for the lifetime of the payment channel. The liquidity of the channel participants is thereby reduced. Wallet. A new wallet or extension of existing wallets may be needed to support off-chain protocols. Let's look for the decision model for on-chain data management. The goal is deciding which data to store on-chain. Characteristics of the data to be managed by the blockchain determine that blockchain should be selected. If the data to be stored surrogate asset ownerships or identification, the tokenization pattern should be used to create and manage digital authoritative records of assets on the blockchain. A token can also be used to represent identity, which is mainly used in security design. When it comes to asset ownership, tokenization reduces the risk of handling high-value digital or physical fungible or non-fungible assets. A legal process in the physical world is required to make the ownership transfer on blockchain an authoritative record. Blockchain transactions ensure authorization creation, transfer, and trading of tokens, enhancing flexibility and cost efficiency. However, the asset represented by the token could be manipulated outside the blockchain without recording the transaction on the blockchain. This compromises data integrity. The blockchain data is accessible to all users on the blockchain network as they have the same level of privileges. If data are supposed to be accessible only by the transacting participants, the encrypting on-chain data pattern, which complements raw data on-chain, could be applied to encrypt the data before adding to the blockchain. We assure that the blockchain platform uses no advanced cryptography, like zero-knowledge proof. However, as the encrypted data are stored immutably, they may be subject to brute force encryption attack in the future. Legal and smart contract peer is a pattern that evolves from the hash on-chain pattern. This pattern provides a bidirectional binding between a legal agreement and the corresponding smart contract to provide an authoritative source to the legal contract. The two-directional binding is based on the hash of the legal agreement and the smart contract's immutable address, thus making sure that the legal agreement and smart contract have one-to-one mapping. State channel only records the opening of the final settlement transactions on the blockchain while handling all intermediate transactions of small monetary value of on-chain in a payment channel. Next group of patterns is security patterns. We will discuss three patterns: multi-authorization, off-chain secret-enabled dynamic authorization, and X confirmation. In the multi-authorization pattern, a set of blockchain addresses which can be authorized a transaction is predefined. Only a subset of the addresses is required to authorize transactions. Problem: the actual addresses that authorize an activity might not be able to decide in advance due to the availability of some authorities. Solution: on the Bitcoin blockchain, A multi-signature mechanism can be used to require one or more private keys to authorize a blockchain transaction. In Ethereum, a smart contract can mimic multi-signature mechanism. More flexibly, an M of n multi-signature can be used to define that M out of n private keys are required to authorize the transaction. Benefits: flexibility. This pattern enables flexible binding of authorities but depends on the availability of authorities when the activity is conducted. Lost key tolerance. One participant can own more than one blockchain address to reduce the risk of losing control over their smart contracts due to a lost private key. In a smart contract implementation of this pattern, there could be a function to update the list of allowed authorities and the authorization quorum. Drawbacks: predefined authorities. Although the pattern enables flexible binding, all the possible authorities still need to be known in advance of any decision or update. Lost key. At least m private keys among the n private keys should be kept safely to avoid losing control. Cost of dynamism. In a public blockchain, if the public blockchain is used, updating the list of authorities costs money, as does deploying the logic for multiple authorities. There is a greater cost for storing multiple addresses compared to only one. Next pattern is off-chain secret enabled dynamic authorization. The off-chain secret enabled dynamic authorization pattern using a hash created off-chain to dynamically bind authority for a transaction. Problem: sometimes the authority who can authorize a given activity is unknown when the corresponding smart contract is deployed or the corresponding transaction is submitted to the blockchain. Blockchain uses digital signatures for authentication and transaction authorization. Blockchain does not support dynamic binding with an address of a participant which is not initially defined in the respective transaction or smart contract. Solution: an off-chain secret can be used to enable a dynamic authorization when the participant authorizing a transaction is unknown beforehand. Benefit: dynamism. This pattern enables dynamic binding of unknown authorities after the transaction is added into the blockchain. Lost key tolerance. No specific private key is required to authorize transactions. Routability. This pattern has the useful property that once the secret is revealed, any other transactions secured using the same secret can also be opened. Interoperability. There is no need for a special protocol to enhance or exchange the secret. The secret can be exchanged in any way off-chain. This provides a mechanism for other systems to trigger events of blockchain. Drawbacks: one-off secret. The secret used in this pattern is an one-off secret. Verification of the secret is on-chain, whereas once a secret is embedded in a transaction submitted to the blockchain, the secret is revealed. Combination of a signature and secret. Because this pattern has the property that once the secret is revealed, any other transactions secured using the same secret can also be opened. Sometimes the transaction protected by the secret should also be associated with the public key, so that both a correct secret and an appropriate signature with the respective private key are required to authorize the transaction. Lost secret. The sender initiator of the transaction takes the risk of losing the off-chain secret. If the secret is lost, the transaction cannot be authorized and being proceeded anymore. Man-in-the-middle attack. A man-in-the-middle attack is possible when the transaction that reveals the secret is in the transaction pool of miners. Next pattern is X confirmation. The X confirmation pattern waits for sufficiently many blocks as confirmation to ensure that a transaction added into the blockchain is immutable with high probability. X confirmation is a pattern for the proof of work, but not necessarily for other consensus algorithms. Problem. At the time of fork occurs, there is usually no certainty as to which branch will be permanently kept in the blockchain and which branch will be discarded. The transactions that were only included in the unsuccessful branches turn off not to have been included in the ledger and will revert to the transaction pool to be added into a later block. Solution. From the application perspective, one security strategy is to wait for a certain number of blocks to be generated after the transaction is included into one block. After this number of blocks, the transaction is taken to be committed and thus perceived as immutable. Benefits. Immutability. The more blocks being generated after the block is included the transaction, the higher probability of the immutability of the transaction. Drawbacks. Latency. Latency between submission and coming of transaction is affected by the consensus protocol, the interblock time, and the number of confirmation blocks. Decision model for authorization. The multiple authorization patterns provide more flexibility to enabling a set of blockchain accounts to authorize a function call. Although this pattern allows flexible binding between the function call and authorities from a larger set of blockchain accounts, all valid authorities still need to be specified in the smart contract. When the authority to authorize an activity is not known in advance, the off-chain secret-enabled dynamic authorization pattern could be used. The function call being authorized is defined with a hash value of an off-chain secret such as random string. Whoever knows of this off-chain secret could then authorize the function call by revealing the secret using a transaction. The smart contract can then compare the predefined hash with the hash computed from the secret to determine the authorization. One constraint of this pattern is that the off-chain secret cannot be reused once revealed in a transaction. As the off-chain secret could be used on different blockchain platforms simultaneously, this pattern improves the interoperability, for instance, Atom's web among blockchains. The next group of patterns are contract structural patterns. They include registry contract, data contract, enabled permission, factory contract, incentive execution patterns. Let's look to registry contract pattern. Before evoking a smart contract, the address of the latest version of the smart contract is located by looking up its name on a contract factory. Problem: smart contract deployed on blockchain cannot be upgraded because the code of the smart contract is a type of data and data stored on the blockchain is immutable. Solution: an off-chain registry is used to maintain a mapping between user-defined symbolic names and the blockchain addresses of the registered contracts. Benefit: human-readable contract name. The registry contract maintains a mapping between human-readable names and the hexadecimal addresses of the smart contracts. Constant contract name. The smart contract associated with the registered name can be updated without changing its name. Transparent and upgradability. The smart contract associated with a registered name could be replaced by a new version without breaking the dependencies based on the human-readable name. Version control. Version control can be integrated in the registry contract to allow a lookup based on the name and version of smart contract. Drawbacks: limited upgradability. Upgradability is still limited if the functions defined in the smart contract are directly invoked by other contracts. Cost: there is an additional cost to maintain a registry that contains the mapping between the contract names and their addresses. Data contract pattern. The data contract pattern stores data in a separate smart contract. Problem: storing data on blockchain is expensive, and there is a limitation of the amount of data and amount of computation a transaction can contain. Solution: to avoid moving data during upgrades of smart contracts, the data store is isolated from the rest of the code. If the context of blockchain, data could be separately stored in different smart contracts to enable isolation. Benefit: upgradability. By separating data from the rest of the code, the logic of the application can be upgraded without affecting the data contract. Cost: since the data is separated from the rest of the code, there is no cost for migrating data when the application is upgraded. Generality: if the data can be cleaned separately and generalized, there would be an additional benefit. The generic data contract can be used by all related logic smart contracts. Drawbacks: cost. If a public blockchain is used, storing a piece of data in a generic data structure costs more money than a strictly defined data structure. Next pattern is on embedded permission. In the embedded permission pattern, smart contracts use embedded permission control to restrict access to the evocation of the functions defined in the smart contracts. Problem: a smart contract by default has no owner, meaning that once deployed, the author of the smart contract has no special privilege to invoke on the smart contract. A permissionless function can be triggered by unauthorized user accidentally or maliciously. Such a permissionless function can be a vulnerability for the blockchain-based application. Solution: add permission control to every smart contract function to check permissions for every caller that triggers the functions defined in the smart contract. Permissions are determined based on the blockchain addresses of the caller. Benefit. Security. Once the participants and smart contracts that are authorized by the smart contract can be called, the corresponding function successfully. Secure authorization. Authorization is implemented in smart contracts running on blockchain which leverage the properties provided by blockchain. Drawbacks. Cost. On a public blockchain, extra code that implements the permission control mechanism also has additional deployment and runtime cost. Lack of flexibility. Permissions are defined in the smart contract before its deployment. Therefore, they are difficult to change. However, permissions may be required to be dynamic. A mechanism is needed to support dynamic granting and removal of permissions. Next pattern is factory contract pattern. In the factory contract pattern, an on-chain template contract is used as a factory that generates contract instances from the template. Problem. Keeping the contract template off-chain cannot guarantee consistency between different smart contract instances created from the same template because the source code of the template can be independently modified. Solution. Smart contracts are created from a contract factory deployed on blockchain. The factory contract is deployed once from the off-chain source code. Benefit. Security. Keeping the factory contract on-chain guarantees the consistency of the contract definition. Efficiency. If the contract definition is kept on-chain in a factory contract, smart contract instances are generated by calling a function defined in the factory contract. Drawbacks. Deployment cost. If a public blockchain is used, using factory contract requires extra cost to deploy the factory contract. Function call cost. If a public blockchain is used, creating a new smart contract instance requires extra cost to call a function defined in the factory contract. Next pattern is incentive execution pattern. In the incentive execution pattern, a reward is provided to the caller of the contract function for evoking it. Problem. Users of a smart contract have no direct benefit from calling accessory functions. If a public blockchain is used, executing these functions causes extra monetary cost. Some accessory functions are expensive to execute. Solution. Reward the caller of the function defined in the smart contract for evoking the execution. For example, sending back a percentage of the payout of the caller to reimburse the gas execution cost. Benefit. Completeness. The execution of the accessory functions helps to complete the regular services provided by the smart contract. Cost. Users who expend resources to execute the accessory functions are compensated by the reward associated with the execution. Drawbacks. Unguaranteed execution. Execution cannot be guaranteed even with incentives. Thus, another option is to embed the logics of accessory functions into the other regular functions that users must call to use the service. Decision model for multiple smart contracts. To maintain a central registry of all smart contracts related to an application, an on-chain contract registry could be used. Such a registry can maintain the mapping between the user-defined symbolic names and blockchain addresses of smart contracts. The smart contract associated with the register's symbolic name could be upgraded by deploying a new version of the contract without breaking the dependencies with other smart contracts. A factory contract could be used to generate smart contract instances from a contract template already deployed on the blockchain. These instances could be customized versions of one or more standard smart contracts coded as a template. Further, a contract registry can be used to record all the contract instances generated by a contract factory. The data contract pattern follows the software design principle of separating data from the business logics. A data contract embeds data and provides function calls to perform create, read, update, and delete operations on embedded data via authorized transactions. Like most of the on-chain patterns, the size of the data on-chain is restricted by transaction size. Data contract pattern increases the cost due to the increased size of smart contract code and added complexity in executing them. Smart contracts are event-based programs that cannot execute autonomously. A transaction of other smart contract must trigger the state-changing functions defined in a smart contract. We may also want to run auxiliary functions asynchronously to perform tasks such as automated dividend payouts and cleanup of expired records. To trigger such auxiliary functions, the incentive execution pattern could be used to provide a reward to the caller of the smart contract function. To further guarantee the execution of auxiliary functions, their logic could be integrated into regular functions calls using the embedded into other function patterns. To summarize, blockchain can be used as a core component of possibly large decentralized software systems. For effective use of blockchain to this end, patent can contain means to make good use of blockchain in the design of system and application. This patent collection includes 3 patterns about interaction between the blockchain and the external world, 4 data management patterns, 3 security patterns, and 5 contract structural patterns. This pattern collection, some patterns in this pattern collection are designed specifically for blockchain-based applications considering the unique properties of blockchains. Others are variants of existing software patterns applied to the blockchain. Thank you for your attention.